There are many examples of objects that rotate, things like the wheels on our car, merry-go-rounds, fans, drills, washing machines, blenders, and it's important that we have the tools to be able to describe the motion of those objects as well. And so we're starting with rotational kinematics, the kinematics of rotating bodies. Let's imagine that we have a tire, and on the outside edge of that tire, which rotates about some central point, there's a red dot. And we want to study the rotation of the tire by looking at that red dot. If we think back to when we studied kinematics previously, we should remember that we studied the motion of objects using a Cartesian coordinate system. All objects existed as being somewhere on the Cartesian coordinate system, which meant they had an x and y position. And so we could imagine a Cartesian coordinate system existing on top of this tire, where these yellow lines represent the x and y axes. And that red dot has an x and y coordinate. If we imagine this tire to be rotating counterclockwise, you should be able to see that the red dot has an x and y coordinate which are both changing. At all moments in time, the x position changes and the y position changes, which can make it pretty inconvenient to describe the motion of that red dot over time, because we have two variables that are changing. And so the Cartesian coordinate system is not used to describe rotating bodies. Instead, we often use polar coordinates. Polar coordinates use the distance that the object is away from the center of rotation, which is r, and the angle that the object makes with respect to the coordinate system. And so maybe where the red dot is right now is 0, and then as the red dot travels counterclockwise, we have some positive angle that the red dot has traveled to. Okay? And you might know that if that red dot travels through a certain arc like this, where it starts horizontally down there and then has moved up and to the left to this point here, and if the angle between those 2 points is delta theta, and the distance that that red dot is away from the center is r, then the arc length, which is the length of this arc, which is made by the red dot as it moves between those 2 points, s, that arc length is given by s equals r times delta theta. And if r is measured in meters, and theta is measured in radians, then we can determine the length of that arc in meters. You should remember that radians describes the ratio between the circumference and the diameter of a circle. So, for example, circumference is equal to pi times diameter, and so pi is equal to the circumference of a circle divided by its diameter, which is always about 3.14. And that number, 3.14, you can think of as being unitless, because circumference would be measured in meters or centimeters, and distance is measured in meters or centimeters, some unit of length, and those two units always cancel, leaving us with the same ratio. And that ratio is given a name, which we call radians. So radians is not a unit, but it's kind of like a placeholder for measuring angles. When we work with angles in rotational kinematic equations, we'll always need to use the angle in radians. But we might be given information in terms of degrees or revolutions, and so there's some vocabulary that we need to get used to, and we need to make sure that we understand the relationships between and among degrees, radians, and revolutions. And so now I'd like to draw another coordinate system and run through some of these relationships which you know about the different ways to measure these angles, radians, degrees, and revolutions. So for example, if I start on the right-hand side, this is the place where theta equals 0 degrees, or theta equals 360 degrees. If I start there, then the angle could be described as being 0, and then if I start there and go counterclockwise through one full revolution, then I will have traveled through 360 degrees. Also, this is the place where theta is equal to 0 radians and theta is equal to 2 pi radians, because one revolution is equal to 2 pi radians. That is, if I start at this point and I travel all the way around this circle back to the same point, then I have traveled 2 pi radians. And by consequence then, if I only go halfway around, if I only make it to this point, then I'm at the point where theta equals pi radians. Or that's also the place where theta equals 180 degrees. And then we can subdivide that any way that we want. If we just go to this bottom part here where theta would be equal to 270 degrees, then we should know that this is the place where theta is 3 pi over 2 radians. And so very important is this relationship between revolutions, radians, and degrees. One revolution is 2 pi radians, and 2 pi radians is equal to 360 degrees. Very often you'll need to convert between these three things. And so oftentimes, instead of saying 2 pi radians equals 360 degrees, what people will write is that pi radians equals 180 degrees. And so sometimes we'll need to convert between degrees and radians, and very often this relationship will be the one that we'll use to do that. And so, for example, maybe I need to convert from 90 degrees into its equivalent number of radians. 90 degrees then would need to be divided by 180 degrees and then multiplied by pi radians. I can use that conversion factor to convert from 90 degrees. 90 times pi divided by 180. 90 over 180 is 1/2. And so this would be equal to pi over 2 radians. And then if we needed to, we could do pi divided by 2 to determine the specific number of radians that we need for a calculation that might matter in a problem. Okay? And so some takeaways from this first part of the video. First, if an object goes through one complete rotation, that is one revolution, and one revolution is equal to 2 pi radians, or 360 degrees. Or we could describe the relationship between radians and degrees as pi radians equals 180 degrees, which could be used conveniently for finding unit conversions between those two. Lastly, I would like to also point out that when we write radians, we write RAD for radians, not just R, because R is already being used for radius. And also lastly, the whole reason why we're doing this is because it's more convenient to use polar coordinates, describe objects using the radius and the angle for things that are rotating. When we studied kinematics before, we talked about a displacement, which I'm now going to call a linear displacement. And linear displacement was given by delta x. So a final position minus an initial position on the Cartesian coordinate system. The difference between those two things could tell us how far the object had traveled. And now we're going to refer to something called the angular displacement. Which, instead of using the initial and final positions on the Cartesian coordinate system, we will use, as I sort of implied previously, the difference in the angles made by the object with respect to the coordinate system. So a final angle minus an initial angle, where those positions might be measured in meters, and those angles should be measured in radians. And so let's say an object travels through a linear displacement delta x, which is a vector, in a certain amount of time delta t. Then we've said that object has a velocity v, which is a vector. And that velocity is given by the units meters per second. And so previously we just called this velocity, but now we might call this linear velocity. And so now we're going to draw the parallel and define a new quantity which we'll call angular velocity. And so the angular velocity is going to be defined not by a change in x position or y position, but by a change in angle. And so the equation is very similar. We have delta theta divided by delta t. How quickly does the object move through a certain angle, delta theta? And instead of writing v for angular velocity, we use the Greek letter omega, which looks like a lowercase letter w. And so because theta is a vector, it could be, let's say, clockwise or counterclockwise, it has a direction to it, then omega also is a vector. And so the equations are very similar, but the units are different. Time is still measured in seconds, and we know that theta will be measured in radians. And so instead of meters per second, our angular velocity will be measured in radians per second. I should also point out that when we're using two positions or two angles which are far apart, then these quantities are all average quantities. And so really this is average angular velocity and average linear velocity. It's quite common that instead of radians per second, an angular velocity will be given in revolutions per minute. So instead of radians per second, we get revolutions per minute. So you can see that the dimensions are the same, and you would need to convert from revolutions to radians and from minutes to seconds in order to have the units be the units that we want, the units that we would use in a kinematic equation for a rotating object. We've also said that if the linear velocity of an object is changing, then the object has an acceleration, or a linear acceleration. And that acceleration, which is also a vector, is given by delta v, the change in velocity over a change in time. And since the units of velocity are meters per second, and the units of time is seconds, then the units of acceleration were meters per second squared. And so similarly now, if an object is not rotating at a constant velocity, if it's speeding up, like for example when we put a CD into a computer and then it speeds up, or if it's slowing down like the rotation of a wheel maybe as a bike comes to a stop, then the angular velocity might not be constant, in which case there would be an angular acceleration. And for angular acceleration, we use the symbol alpha, okay, the Greek letter alpha, which looks like that, looks like a little fish. Alpha is also a vector, and this vector, alpha, which represents the angular acceleration, is, it has the same form of the equation as the linear acceleration, and so it's not delta v, but delta omega over delta t. And so if omega has units of radians per second, and time has units of seconds, then we'll have radians per second squared as the units for the angular acceleration. And so rather quickly I've defined a lot of new equations, but what I want to point out is that the equations are very similar when you look at the linear and angular quantities. And so for linear displacement, we have delta x equals final minus initial position. And for angular displacement, we have delta theta is final minus initial angle. For linear velocity, we have the average velocity is the change in position divided by the change in time, which is given in meters per second. And for angular velocity, the average angular velocity is given by change in angle, delta theta, divided by change in time, delta t, and that's measured in radians per second. And lastly, linear acceleration, which is a, is equal to change in velocity divided by change in time, which has units of meters per second squared. And angular acceleration, which is represented by the symbol alpha, is change in angular velocity, delta omega, divided by time, and it has units of radians per second squared. As we continue to study rotation, you'll find that this little divide that I'm making here between the linear or translational quantities and the angular or rotational quantities, there's going to be a long list. Right now we have three things: displacement, velocity, and acceleration, but there are all sorts of quantities taking us all the way up to things like momentum, where there will be a very similar quantity that we can use our understanding of linear quantities to help us sort of organize our thoughts about how rotational motion works. Lastly, I'd like to do an example which sort of ties all this together. A CD is rotating at 50 radians per second when the eject button is pressed, causing the CD to stop rotating in 0.8 seconds. The radius of the CD is 6 centimeters. The first problem says to find the average angular acceleration of the CD as it slows to a stop. As I showed previously, the average angular acceleration, alpha, is given by the change in angular velocity divided by the change in time. And so this can also be written as the final angular velocity minus the initial angular velocity divided by the change in time. The final angular velocity, if the eject button is pressed and it causes the CD to stop, up above they say that it stops, and it starts at 50 radians per second, then the final angular velocity will be 0, and the initial angular velocity will be 50. The change in time, delta t, is given by the 0.8 seconds. And so 50 divided by 0.8 is 62.5. So negative 62.5 would be the angular acceleration, where negative means that the angular velocity of the CD decreased. And lastly, angular acceleration has units of radians per second squared. And so my final answer for question number 1 is negative 62.5 radians per second squared. The second question asks, find the linear speed at the rim of the CD before the eject button is pressed. So if I imagine a picture of the CD, something like this, then the center of the CD is here, and if the radius of the CD is 6 centimeters, then we're talking about a point which is 6 centimeters away from the edge. And 6 centimeters is also 0.06 meters. And so how do I figure out the linear speed, which is not omega, but v, at that point? I'm trying to find what the linear speed is, v, at that point. So omega, if you want to imagine how that could be drawn on this picture, omega could be this blue arrow here. Omega points in a direction which would be in the direction that that red dot would be traveling. But what I'm being asked is to find the linear speed, the tangential speed, v, which is tangent to this point. And so in order to find what this linear speed is, I need to somehow figure out what the relationship is between the radius, the angular speed, and the linear speed. I know that in general this tangential speed, which I've drawn in red in my picture, vt, is related to distance and time in the following way: distance divided by time. And for an object that is traveling around in a circle like that about the rotation of the CD, the distance that that point would travel as it goes through one complete revolution would be 2 pi times r, the radius. And the time that it takes to do that is the time that it takes for one full revolution, which is also referred to as the period, capital letter T. And if I write that in a slightly different way, if I write it as r times 2 pi divided by t, we should see that 2 pi is the delta theta for one revolution, and capital letter T, which is the period, is the delta t for one revolution. And so 2 pi divided by delta t is the same thing as angular speed, which is omega. So that tangential speed or linear speed, which I've drawn in red in my picture above, vt, is related to r and omega in this way. Vt equals r times omega. This is a very important relationship. The linear velocity is related to the angular velocity through this relationship. And also another important relationship which relates the angular and linear accelerations is a equals r times alpha. These relationships, I'll only use one of them now, are both incredibly important because it allows us to relate linear and angular quantities through the radius, which is often a given piece of information. And so if this question asks me to find the linear speed at the rim of the CD, then I just need to know the radius, which was 6 centimeters, or 0.06 meters, and the angular velocity before the eject button is pressed, which was 50 radians per second. So times 50 radians per second. And so here, 50 times 0.06 gives me an answer of about 3. And here, the answer that I'm getting here is for the linear speed, that point that I've drawn in red. The linear speed would have units of meters per second, not radians per second, because I wasn't looking for the angular speed. And so there are a lot of important things that this problem pulls out. There's a relationship between linear and angular quantities. V equals r times omega, a equals r times alpha. The units of angular quantities always need to have our angles measured in radians, or our angular velocities measured in radians per second. And when I'm working with rotational problems, sometimes I'm still asked about linear quantities like linear speed, in which case I need to remember that the units are meters per second, not radians per second.